So good day everyone. We will be having a CFD tutorial about a oscillating hydrokinetic turbine. In this case, a single foil in a two-dimensional setup. So before we begin, we will be having a short introduction to oscillating hydrokinetic turbines, and later on we'll be have a short discussion as well of the results. In a world-driven economy, the rise of price of gas and other fossil fuels consequently makes some renewable energy sources economically viable. Moreover, the renewable energy sectors are now more and more seen as a serious business opportunity. Some of the most popular renewable energies include solar, wind, and tidal energy. The huge potential of tidal and in-stream renewable energy has been assessed by numerous studies in recent years. Hydrokinetic turbines are being developed to produce electricity from the kinetic energy of flowing water. These dampless or zero-head turbines are thus very analogous to wind turbines. However, the hydrokinetic energy offers several advantages compared to the wind. The most important are a greater energy density and a much better predictability. Inspired from wind turbine industry, most of the hydrokinetic turbines proposed are based on horizontal and vertical axis rotor blade designs. Although the concepts based on rotor blades benefit from experience gained in the wind turbine sector, other designs might be better suited for the hydrokinetic application, and the oscillating foil hydrokinetic turbine is one of such designs. And moving forward to the governing equation, as you can see in the schematic diagram, the foil's movement is represented by a heaving and plunging motion. The plunging motion is represented as ht, where the amplitude or limiter is h0. The pitching motion is represented by theta t, and its amplitude or limiter is theta 0. The, the stream velocity is represented by u infinity, while d is the total distance traveled by the foil, and c is the chord length. The pitching motion is represented by the following equation, which is the theta amplitude multiplied to the sine of the angular frequency multiplied to time. And its first derivative is as follows. And the ht, or the heaving motion, is represented by the following equation. Ht is equals to the heaving amplitude multiplied by sine of the angular frequency multiplied to time plus the phase angle. And the first derivative is as follows. The relevant angle of attack, on the other hand, represents the angle made by the foil when it interacts with the effective velocity of the flow. Having that said, we can now create the instantaneous power equation, which is simply the lift multiplied to the foil's displacement speed and the moment force multiplied to the first derivative of the pitching motion. Cp, which is the non-dimensional equivalent of the instantaneous power, can be equated as the following, and its conversion factor is simply 1/2 times the density of the flow times the velocity of cube of the flow and the foil's span and the c chord length. The percent efficiency of the power can be equated as the instantaneous power divided by the available stream power. And the following parameters were chosen in the study, having three cases for the control hydrofoil, NACA 0015, which is a symmetrical foil. A power extraction regime of CP from a study by Kinsey and Damas was also referred in choosing the parameters. So why choose flapping foils? First, the whole foil travels at a constant speed, allowing a higher proportion to the surface of the foil to be used for optimal power extraction. Flapping foils may be installed in shallow waters and scaled up more readily than rotational turbines, which is limited in deep depth because of the protruting blades rising over the water surface. A smaller model would mean a higher power output due to increase in the number of turbines in a farm. And lastly, oscillating hydrokinetic turbines optimize area and have a higher filling factor than that of circular or rotary turbine. The turbulence model used in the study is the URANS, or the Unsteady Reynolds Average Navier-Stokes. It is a method in use in CFD, or computational fluid dynamics, to solve the time-dependent Navier-Stokes equation, which govern the motion of the fluid. The Navier-Stokes equations are set of the differential equations that describe the conservation of mass, momentum, and energy in a fluid. Urans also uses Reynolds average approach, which involves averaging the fluid properties over a characteristic time scale known as the Reynolds time scale. This allows for separating the fast-varying turbulent fluctuations from the slow-varying mean flow. By averaging the equations in this way, the Urans method can capture the essential physics of turbulence, such as the Reynolds stress and turbulent transport, while still allowing for the use of relatively simpler models. Lastly, Eurance is a commonly used method for industrial purposes due to its balance between computational costs and accuracy. So the following equation represents the conservation of mass and the continuity equation. And for the momentum equation, an infinitesimal control volume, the moving fluid element is subjected to two different forces, surface forces and forces. And as you can see, the following are the equation for the momentum equation. So in the study, we also compared different solvers, which namely are the Spallert Armaros, the K omega, as well as the K epsilon, compared to that to a related study of using another solver, which is also a Spallert Armaros by Kinsey and Dumas in 2011. So the Spallert-Armaros model is a one-equation model. It only solves a single equation for the turbulent kinetic energy, rather than a set of equations as of the other turbulent models K epsilon or K omega. This makes it a relatively simpler model to implement, which is one of the reasons for its popularity. It is a model that also employs the principles of Galilean invariance, which means that it can predict the correct behavior of flow regardless of the reference frame in which it is observed. This is a desirable property for turbulence model, as it allows the simulation of flow with complex geometries and moving boundaries.
Hello guys! Before we can proceed to the ANSYS setup, we should start with the hydrofoil geometry. To do that, let us get the coordinates of NACA0015 in airfoiltools.com. Just look for the search bar and type in NACA0015. Choose the first one that appeared in the web page. In here, you can see the overall shape of the foil, and if you can scroll down, you can see the other aerodynamic properties that people got from their test. Now, let us proceed to open that file. Choose the Selig format and the coordinates will appear. Let us copy the coordinates to Google Spreadsheets. As you can see, the coordinates are in one column. To separate them, go to the data ribbon and choose split text to columns. Since this simulation is in 2D, we'll only be needing the values in the X and Y directions. In column E, let us put 0 for the values of Z. In column A, let us put 1. And in column B, let us put in another 1 followed by a 2 and drag down these values. Let us now download the file to tab separated values format. In downloads, let us rename the file to text. Now that we have the coordinates of the hydrofoil, we can now proceed to ANSYS. In your computer, open ANSYS. From the sidebar, choose ANSYS FLUENT. Now, let's sketch the hydrofoil as well as the boundary conditions of the simulation.
The foil, go to Concept and then select 3D Curves. Upload the text file of the hydrofoil.
Now, let's create the inner boundary condition for the non-conformal interference. Additionally, let's create the fixed mesh or the outer boundary condition for this setup. Let us also make each boundary independent from one another by creating a boolean. Let's now create intersecting lines that are parallel to our circle where the rotating mesh will be placed. This will also help us to refine the accuracy of our structure-flow interaction. Let us also refine the dimensions of our outer boundary. Aside from the outer boundary, let's also refine the dimension of our inner circle where the rotating mesh will be placed. In this part, we need to divide the outer boundary to 4 triangles through Boolean to refine the accuracy of the flow when we start ANSYS FLUENT. To make our lives easier when we get to ANSYS FLUENT, let us now name each of the boundary sides of our setup. In our study, we wanted to replicate the results of the study of Kinsey and Dumas from 2012. In this particular setup, I created their mesh 1, which is the coarse mesh. Their paper specifically identified the coarse mesh to be around 17,000 elements. But due to constraints in computing resources as well as time, I will create a mesh with less elements. Additionally, the number of nodes in the hydrofoil for this setup is around 250. In this part of the setup, we will be able to appreciate the use of a non-conformal interface. Typically, it is used in ANSYS FLUENT when modeling multi-component or multi-domain systems with complex geometries. Non-conformal interfaces allow for the efficient and accurate simulation of fluid flow across different domains with different mesh resolutions and topologies. For the case of this setup, the use of a non-conformal interface is to model complex geometry, such as this one with internal obstructions or moving parts. In such cases, it may be difficult to create a single conformal mesh that covers the entire geometry, and a non-conformal interface can be used to connect separate meshes and simulate the flow across the different domains. As I mentioned a while ago, our setup has a moving mesh, specifically a rotating one. To enable that, we will be using a user-defined function or a UDF. So, a UDF is a customized piece of code written by the user like us in the C programming language. It is compiled separately and loaded into ANSYS FLUENT, where it can be used to define various features of the fluid flow. In the screen, you can see the user-defined function we have used. So for our case, the UDF is used to define the specific boundary conditions such as the velocity profile. It is also very important since the movement of the foil is coded in the UDF, and you can see here the varying parameters we use such as the reduced frequency and the heaving amplitudes. The UDF that we are using is actually from the study of Kinsey and Dumas, and we just made a little bit of modification since the original code was written in ANSYS 2012. Now let us proceed to ANSYS Fluent. Open the setup and we will be specifying the general parameters used in the study. We'll also load the UDF that we modified in ANSYS 2021. Once the mesh is successfully loaded to the setup, we can now start specifying the parameters we needed in this study. To make this tutorial possible, we will be using the one equation Spallert-Almaraz turbulence model since it does not require too much computing power, yet delivering satisfactory results. Let's now proceed to how we generated the results. We will be getting the results of the time-varying velocity vector from the top boundary side. For this simulation, we will be using the number of time steps to be at least 100,000 with a time step size of 0.004 to get accurate visualization of the flow. Aside from that, you will also be conducting a maximum iteration of 1,000.
Coefficient of lift versus non-dimensional time. There are a few observations that can be made from the CL versus T graph. The graph starts at a short downward slope, and after a few values, the slopes start to go upward, with some noticeable fluctuations at around values of 0.5 to 0.6 in the y-axis. These unstable points are experienced due to stall conditions of the foil, specifically during its stroke reversal. The lowest point in this graph is at around the y value of 0.1, while the highest CL value is 2.828. For the coefficient of moment versus nine-dimensional time, the values are demonstrated through this graph. As observed, there are noticeable variations on the slope, specifically between 0.4 to 0.7 y values. This would indicate the fluctuations experienced by the foil because of stall conditions, similarly to the CL versus T graph. The highest CM, or coefficient of moment value experienced by the foil, is at 0.594, and it has a mean value of 0.054. for the coefficient of power and percent efficiency versus non-dimensional time, the symmetrical profile of the foil leads to a consistent peaks and trends for the upstroke and downstroke power coefficient, and the percent efficiency results by the foil. From the graphs, each also has three lowest points that occurred almost at the same time. The peak result for the power coefficient is 3.843 with a mean value of 1.194. The percent efficiency versus time, on the other hand, has 1.406 as the highest value, while its mean is at 0.597.
Flow visualization is an integral part of our study. After getting the numerical results for the coefficients of lift, moment, and power, we now proceed to the setup of the animation of the movement of the hydrofoil. Let's go back again to the setup, and we should first initialize the simulation before the animation setup. For the flow visualization, it is helpful if we use contours to locate where are the separation of the flow happening in the surface of the foil. After the solution is complete, we can now see the animation created by ANSYS FLUENT. At this part also, we can specify the format of the file we wanted for the flow visualization, and we are choosing a video format. For the entirety of the study, we did all this setup for at least 16 times, and after those setups, we can get the numerical data of the parameters we needed as well as the flow visualization.
Moving on to the flow visualization, these four images are presented for the flow visualization. The first image being the representation of the beginning of the cycle of the foil. The second image represents the 0.25 second time of the cycle, where the downstroke power generation occurs. Next one would be the foil's lowest point, which is the minimal power generation. And the last image is where the upstroke generation occurs. Based on the presented images, especially the first and third visualizations, the flow around the foil has incomplete wake vortices formation, and not as smooth as the other cases 2 and 3. And it is also clearly observed that the foil is struggling. These may lead to fluctuations in the data in lift and moment force generation. With the utilization of CFD or computational fluid dynamics, the study was able to investigate and compare the effects on power generation of varying foil geometries that are biomimetically inspired for a full passive oscillating turbine. It gave insight on how the chosen parameters could affect the foil's performance through increasing the frequency and or heavying and pitching amplitudes. The CFD results gave insight to the study on what possible ways we could improve and test concepts before implementing to a laboratory model, thus diminishing the total scope of experimental tests to be made, focusing on key important changing parameters. Thank you.